expressive behavior data set. Because we will work on that one first. Because we went through and did all the screening for this, right? And then we did the omnibus test for this, correct? I think that's okay. So what I'm going to do is I'm going to go through and run this real quick. But while I'm doing that, so this is stuff that you already got, so you don't need to worry about following along here necessarily. Questions about how's the problem set going? Good. Questions on anything from that we can address right now?
So for number one,
yep.
Do you want us to do that by hand?
Well, yeah, you have to do everything by hand.
Okay.
So, yeah, go ahead and do that. I guess you could use your calculator to go through and run some of the t-tests. Do them by hand, just so you can go through and work through that process, but definitely use your calculator to double check that.
Okay. Okay.
Any other questions? Okay, so Laura's got the ANOVA set back to me. I will go through and score that. Laura, anything in particular that you saw that were kind of consistent, things that came up in that set in your initial pass that we should probably maybe touch on as people are working through the factorial design stuff?
I'm sorry?
Oh, I was saying, I said that you'd gone through and done, I need to go through and score things that you got those sets back to me. Anything that you saw that was systematically came up as an issue on the one-ways that might be relevant to the stuff that they're doing right now?
I can't think of anything that would be relevant.
Okay, okay, cool. So I'll go through, get those scored, get those back to you so that you all have those to work from, okay? So what we're gonna do, I've never been in this position before. We've got the whole class period to go through, and we're just work through different examples, different looks at what these factorial designs might look like, different considerations and things like that. So we'll spend today doing that. So we had finished up last time looking at what was our cover story on this? Okay. So interested in expressive regulation on physiological activation, blah blah blah. So we had said we'd had people randomized to view one of two affectively valence films, either sadness or humor, under instructions to inhibit expression or just watch it as just naturally. And the question is, what we want to do is run a manipulation check to see whether or not these instructions or whether or not our manipulation to inhibit expression worked, right? So what we did is we videotaped everybody watching as they were watching these videos and had someone outside of sort of the study go through code expressive behavior, just global expression on a 1 to 5 scale, right? And what we want to see, the question is whether or not individuals told to inhibit response demonstrate lower levels of global expression, okay? So we went through, we screened, we did all that stuff, and then we ran our analysis. And so Chrissy, can you tell me what we determined based on this 2x2 ANOVA here?
So
it's on your sheet too, the 2x2 ANOVA. If you're having a hard time seeing.
yeah, I'm still working on getting it going on the computer. So it seemed like there was main effect of film and a main effect of destruction.
Perfect. Main effect of film and main effect of destruction.
Which is good because they did the things we wanted them to.
Yeah, yeah. And how do we, what was the determination? How do we determine main effective film, main effective instruction. How can we interpret that in this set?
So we can basically determine that it seems like when there was a music film, emotional expression was higher.
Okay.
And when there's a sadness film, it was lower.
Okay.
And then with the instruction condition, when people were told to express their emotion, it was higher. And when they were asked to withhold, it was lower.
Okay, perfect. That's brilliant. How did you determine all that?
I looked at the means.
Okay, and how can you interpret these main effects just looking at the means?
So I saw that I saw the p-value first, and then of film and instruction, and then I went to the means to see which one was higher.
Right. Will we always be able to interpret a main effects by just eyeballing the means?
No.
Yeah, why not?
Well, it just depends on what you're measuring, I guess.
Yeah. So what's what?
There can be an example where the mean of each main effect are the exact same.
Okay.
But the interaction.
Okay, so that might be where we have an interaction but no main effect. What if I have 3 levels to my factor? Can I just eyeball the means and make a determination based on that? No, right? So what we're able to do, because this is a 2x2 factorial design, if I have a main effector film, there's only 2 groups. There's only 2 levels of factor A. There's only 2 levels of factor B, right? If there's a main effect, it means that one's higher than the other one, right? And so I don't need to go through and do follow-up tests necessarily to figure out what's actually going on with that effect. With only 2 levels, if there's a main effect, I can just look at them and say, well, this one's higher than that one. All I need to do, that's all I need to do at that point, right? So here we see we've got a main effective film with an F of 30.684. That p-value is telling us that there's considerable evidence against the null hypotheses here. We got our partial eta squared. What if I don't like F's? What if I wanted a T statistic? What are my options here?
M is equal to T squared.
Yeah, right. Under what condition?
Under covariance.
It's true.
And then degrees of freedom is 1?
Yeah, 1 degree of freedom, right? In this situation, right, because I've got 1 degree of, this is an F with 1 and 185 degrees of freedom in the denominator, just because there's only 1 degree of freedom in the numerator, telling me that I'm just comparing 2 levels, I could take that F, and I could take the square root of that and turn it into a T, and that's just going to be a T statistic with 185 degrees of freedom, right? So I could move that back and forth. So if I was reading the paper and I wanted to know what the effect size was for the effect size of film, right? But they didn't give, because these folks are bozos, didn't give me standard deviations, cell numbers, and things like that. I could still reverse engineer this. I could take that F, I could take the square root of that, because I know it's the square root of this F is equal to a T statistic with 185 degrees of freedom, and then I can take that T statistic back translated into a D, and so just knowing how these things sort of work back and forth can be very helpful, okay? So did we, for this problem, I don't think we did, so it's giving us partial eta squared. Did we calculate omega squared, partial omega squared off of this? Okay, let's do that quickly. So someone tell me, how do we interpret partial eta squared? Someone give me an interpretation of the partial eta squared for the effective film. Yeah.
It's the proportion of the variance is accounted by that factor.
Okay.
So it's like 14%. In this instance, it's like 14% of the variability within the sample is accounted for by effective film.
Okay, that's beautiful. Where's Chris off by just a little bit if we're talking about partial omega squared or partial eta squared?
It's the stuff that's unaccounted for.
Okay, it's the stuff that's unaccounted for. That was a perfect interpretation of eta squared, okay, right? But what we've got with this factorial design, what we're often working with is our partial coefficients, right? So this is partial eta squared. That says that of the variability in expression that's left over after we account instruction and film by instruction interaction. After we take that out, this is partial A squared is that film is accounting for about 14% of what's left over, okay? And so I tell you not to sort of come up with magic word interpretations of things. Like I want you to understand things, not just repeating incantations, right? But if we're talking about partial eta squared, partial omega squared, talking about the residual variance, right? And this starts to become important. This is what differentiates partial eta squared from eta squared, is that we're talking about, so here I would say, based on these data, it appears that film accounts for about 14% of the residual variability in expression ratings after accounting for effects of film and the film by instruction, or the effects of instruction and the film by instruction interaction, okay? So again, remember, we've got this piece of the pie. My model overall, if I go through and I take a look at this corrected model, right? This is kind of like an R squared. This says, does this model account for some non-zero level of proportion of variability in an outcome, right? And so that's saying that here's film, here's instruction, and then here's the interaction, right? If I'm wanting to look at, this is factor A, factor B, and this is A times B, okay? Tomorrow, if I'm interpreting eta squared for factor A, what portion of that Venn diagram is being accounted for by eta squared? If I go 1, 2, 3, 4, 5, if I do that, okay. If I say eta squared, 1 and 2, okay. Because eta squared is just of the total variability in my outcome, how much of that is associated with factor A, okay? And if I was calculating eta squared for B, it would be 2, 3, and 4. Eta squared for the interaction would be 5 and 4, right? But if I'm looking at my partial coefficient, partial eta squared, it's what I'm just looking at is 1 relative to sort of all this other stuff, right? And so in general, Nick, if I'm thinking about eta squared and partial eta squared, which one, all things being held equal, is going to be higher, larger? What's that?
Eta squared.
Okay.
Partial eta squared.
Partial eta squared.
This is
Yeah.
a facial reaction.
Just because so my facial reaction. But what else?
Because
What's a bigger number, the total variability or the residual variability? The total, right? And if that's going in the denominator, right? This is why our partial eta squared is always going to be bigger. Partial eta squared is accounting for, if I say eta squared is going to cover 1 relative to the whole piece of the pie, right? Partial eta squared is going to cover 1 relative to just that, right? So after we take out stuff that's we can attribute to A or to B and the A by B interaction, pull that out, now all of a sudden that's about half, right? Versus maybe a third of the full piece, okay? So when we're talking about partial coefficients, partial eta squared, partial omega squared, we're talking about the proportion of residual variability being attributable to some factor, okay? And so, one last thing before we jump into what's the distinguishing? How do we distinguish between eta squared and omega squared?
versus population.
Sample versus population, right? We know that our eta squared statistics are always going to be positively biased, right? They're never going to be 0, even if the population effect is equal to 0, right? And so our omega squared statistics give us a better. They're still a little bit positively biased, but they're not an unbiased statistic, but they're better. But they're better than our what?
Sponges are better.
What's that?
Sponges are better.
Is it figure out if that was, what marker was terrible. Okay, cool. So, let's for, okay, we dropped a permanent marker on this. Okay, if we calculate partial A squared, remember that our formula here is going to be degrees of freedom, whatever our effect is that we're interested in, times F for our effect, minus 1 over degrees of freedom effect times F effect minus 1 plus total number of people in the sample. This is actually pretty easy to go through and calculate. Okay, so if we want to go through and calculate partial omega squared for our effective film, what's the degrees of freedom effect of the degrees of freedom for my film effect? 1, right? And what's my F, the value of my F statistic for that effect?
684.
684. 3.684 minus 1 over, everything divided or multiplied by 1 is itself, so we go 30.684 plus 189 gives me an omega, partial omega squared of 0.136. And Alicia, how does my partial omega squared for my main effective film, how does that relate to my, how does that compare to my partial eta squared? In your output.
Sorry, where are we?
So in your, you have your, okay, yeah. So in the output, it's giving you partial eta squared. How does a partial eta squared for film relate to our partial omega squared for film? Lower. Does that make sense? Why? So conceptually, Chris, I saw you nodding. Does this make sense?
Yeah, because omega, partial omega and omega squared are more conservative estimates because they're doing it for the population.
Exactly, right? Remember that partial eta squared is going to be a biased statistic. We're concerned that it's going to be too big. And so the whole reason we would run omega, partial omega squared, is because it's going to be a better, more conservative, less biased estimate of the population effect. So we would expect that partial omega squared to be smaller than omega squared. Now it's not smaller by much. Why might that be?
Sample size?
Yeah, exactly, right? We're going to see less of a correction as our sample gets bigger and bigger and bigger. As our sample starts to get bigger and bigger and bigger, we're assuming that it's a better estimator of the population effect, right? So if we're working with really, really small samples, you're going to be see a noticeable discrepancy between your omega statistics and your eta statistics. Here, it's not quite as much, okay? So if we were to go through the same process and look at partial omega squared for my main effect of instruction, it's going to be similar. It's going to be 0.135, and then my partial omega squared for instruction by film is going to be 0.013. Okay. And then if we go through, we could calculate eta, just basic eta squared for film 0.124, 0.123. expression going to be 0.014. Sally, can you give me an interpretation of eta squared here?
So there's smaller than partial eta squared.
It is smaller than the partial eta squared, right? So if you just had to look at that and tell me what that eta squared for film, how to interpret that, how would you interpret that?
The residual variability, because it's smaller, going to have
Okay.
larger effect size.
Hold up. So this is eta squared, not partial eta squared. So what piece of the variability are we talking about with eta squared?
You're looking at the observed variability in all of the outcomes.
Exactly.
So
Okay.
it's going to be smaller because of that.
Right. And so how would we interpret that eta squared value of 0.124?
It's smaller, but it's still similar.
Okay. So if we want to can someone help us out with practical interpretation? Yeah.
Can I just repeat what I said earlier?
Yeah.
12% of the overall variability in the sample can be counted 4 by film.
Yeah. Okay. Cool. So this is, I mean, your eta squared is an association effect, right? It's not it's not different than like an R squared statistic type of thing, right? And so eta squared is nice because it's easily interpretable, right? They say, oh, 12% of the total variability in some outcome is attributable to this thing. Makes some sense, right? But what ends up happening as we start to add additional factors into our design, what does eta squared do? It's smaller and smaller and smaller, right? Because we're going to have almost always we're going to have at least some degree of overlap, right? As we start sort of chipping away at sort of the overlap of this, eta squared doesn't get for film doesn't get credit for this little piece right here because that's kind of overlap. It's just sort of random stuff. But it starts to chip away. It starts to make that smaller and smaller. If we're not an experimental person, right? If we're using these models for individual difference characteristics, pre-existing types of stuff, a lot of times, particularly in clinical, the characteristics that we're measuring are overlapping quite a bit, right? If I'm doing experimental work and everything's randomized, these are fairly orthogonal, right? But as soon as I start using these designs for existing factor stuff, what can happen is these start to get smaller and smaller. So our partial eta squared and our partial omega squared end up being better effects to go through and compare across different studies, across different designs. The problem being is that residual variability after accounting for other stuff is kind of a hard thing to wrap my head around. It's a technically correct application, but if I want to say, is this good or bad, you know, we can look at small, medium, large effects. But total variability in some outcome that I'm familiar with, I can sort of envision that in my head. Partial variability after I account for 1, 2, 3 different factors. So I don't know how much is left over, what those other factors are going on. So it's a little bit more difficult to kind of think about conceptually, but it's still an important thing. Okay. Questions on any of this? All right. Anything else that I wanted to calculate here? Okay. So let's say, do we need to go farther with these analysis? Based on my research question, have I answered my research question? What do you think, CJ?
I think you're probably good.
Yeah, because the concern was my manipulation effective? Well, it looks like, yeah. On the whole, we're seeing that people who were instructed to inhibit expression are demonstrating less expressive behavior than people who were allowed to express freely. Okay, so that looks pretty good. But we've got this interaction effect, right? And it's not convincing evidence for a dependency between film and instruction, but it's starting to get within the vicinity of something that traditionally we might want to look at, right? If we look at an S value and a base factor for that effect, the interaction effect. S is going to be 4, base factor going to be 2.10. So not terribly convincing evidence for a dependency of film by instruction, right? But for the purpose of this, just to sort of like give a demonstration for if we wanted to follow up, if we wanted to go through and take a look at that, how we might approach breaking down that that film by instruction interaction. Okay. So first thing we do, anytime we find anytime we have an interaction effect, what's the very first thing we do? Yeah. Graph it, absolutely. Okay. So if I go through and I say, all right, I've got express, withhold, and I've got sadness, film. Now you're going through and SPSS will give you marginal means. Go ahead when you're plotting this, just use your observed means. Your marginal means are adjusted, you're observed to what you're actually seeing in your data. So you want to go through, and I would recommend plotting out your observed means. And so if we look at this film by instruction interaction, we get 1.96. 1.96 for sadness express, 2.98 for amusement express, 1.45 for sadness withhold, and 1.96 for humor withhold. Okay. So then we can go through, highlight that, go through select. I'm going to choose graph here. All right. Do I like the way that this chart is set up? If I'm trying to think about this interaction effect, is this a good way to lay this out? What do you think, Tamara?
It's probably a better way.
What's up?
There could be a better way, maybe.
Maybe. What might determine, because, and again, in Excel, I can go through, and I can highlight this, and then up here, switch column and rows. I can flip that, and now all of a sudden we got a different, what did that do tomorrow in terms of our graph?
I didn't see what happened.
All right, ready? Watch.
Sorry.
Watch close. Ready? Zah! What did this do?
It flipped.
Yeah, it flipped around, right? So this starts to become important, thinking about how do we want to go through and think about and talk about this interaction if this was something that we were going to go through and take a look at. So we see that based on our main effects that our instructions to inhibit is going to result in less expressive behavior, but does this reduction depend on the type of stimulus that's presented, right? So in this case, we know that with the withhold express is going to be sort of we tell people withhold is we're going to have a better sort of a more reduction here, right? But what we might want to know is, does that difference or does that reduction in expression when we tell people to inhibit their expression, does it depend on the type of stimulus that they've presented with, right? And this kind of makes sense, right? Well, it does to me because I've done this work, right? But if you ask people, where do we get a higher level of expressive behavior? And things that are really funny or things that are really sad? Things that are funny, right? We get smiles and things like that, right? Sadness, I can sometimes beg, I don't know, Nick, are you sad? Or are you like, what's, because you got kind of a blank sort of thing on. So like inhibiting the absence of expression is sort of not really doing much of anything, right? So maybe what we want to know is, okay, yeah, our manipulation worked, but I mean, do we see greater levels of greater reductions in expressive behavior if I'm presented with a very sad material versus happy material, right? And so if we set it up here, we're saying, okay, how much of a reduction do we get across express withhold for sad versus express withhold for humor films here, right? Now, we could because these interactions are interchangeable, we could go through and take a look and look at that, right? And so now we're saying, if I'm looking at this graph, I'm saying, well, for those individuals who were told to express, do they express more do they demonstrate more expressive behavior? What's the difference across sadness and humor manipulation for people who were told to express, and for people who were told to withhold expressive behavior across sadness and humor films here, right? That seems like, to me, like a less interesting question, right? For people who we tell to express behavior, do we get more expression in the sad film versus the happy film? Or for people to withhold, more expression in the sad versus the happy? Yeah, I mean, it's sort of interchangeable, but it feels like that this is maybe the more interesting, sort of theoretically relevant comparison. Do we see differences in express versus withhold in our sadness group versus our humor group? Okay. People following me with this? This is the hard thing when we think about, when I told you need to have a game plan before you just jump in the middle of stuff. This is what I'm talking about. How do we go through and represent and present our interactive effects in a way that makes sense? When we start to talk about moderation, this starts to become important. What's the moderator here, right? Is the moderator film condition, or is the moderator instruction condition, right? I would make an argument based on these data that's probably more interesting to see whether or not we see different levels of reductions in behavior for expressive versus withhold for people watching sad, exposed to sad type of stimuli versus people exposed to sort of more humorous stimuli. How many reasonable comparisons, how many interpretable comparisons can we make based on these data? What do you think, Alicia? Okay, sadness, or we can say, okay, we can make these comparisons. For within the sadness condition, we can compare express withhold, and in the humor condition, we can compare express withhold, right? What other comparisons would be reasonable to make within this interaction? Yeah, and what would that look like here? What are the specific comparisons I'm making here? What's that?
The humor compared to the expression.
Okay, humor and expression. So these are different conditions. So if we're doing within sadness, comparing express withhold, and within humor, express withhold, right? So that's two comparisons. What are the other two that we can make? For what?
I can write these out, but like.
So what bars would I compare in the other one?
So you compare the blue to the orange, and the blue to the orange, and the blue to the blue, and the orange to the orange.
There we go. Okay. And use colors, right? We color code things. But this starts to become important. You want to be able to sort of communicate and sort of verbalize, sort of put into words what you're doing here, right? We can go through and we can basically, within each one of our film conditions, we can compare sadness express, or excuse me, humor, or express withhold for sadness, express withhold for humor, right? We could also, for the express condition, we could compare, or for the express condition, we could compare sadness to humor, and then with the withhold condition, we can compare sadness to humor, okay? How many total comparisons could we make within this? How many, like, if physically, how many comparisons are there available within this 2x2 interaction? 6. There we go. So we got 6. CJ, how did you know it was 6?
Colors. I just looked at we talked about the comparing expressive withhold, and the sadness and humor, and then you can compare the express, withhold, withhold across the conditions as well as express, withhold, express. That doesn't really make sense unless a point.
Yeah.
But
Okay. What we can do is there's two comparisons in this 2x2 interaction that doesn't make sense, right? I could physically compare sadness expressed with humor withhold, right? Those are two cells that I could see if there's a difference in there. Does that make sense to compare those two? No, there's not an interpretable effect. Same thing, I could look at sadness withhold, humor expressed. That doesn't make sense to go through and do this, right? So we've got 4 total comparisons that we could make, right? What comparisons are going to be most important to answer our question? Does the impact of expression differ across for people if people are presented with positive stimuli versus negative stimuli?
We're just talking about it on this, looking at the sadness. So like the express from sadness to the
Here.
humor,
Uh-huh.
blue bar to blue bar, orange bar to orange.
Okay, so we've got 4, we could go, sad, express versus withhold, and we go, actually, sad, express versus withhold. We got humor. And then we've got for So we decided, I decided, that within this interaction, it makes more sense to me to want to know what is the effect of stimuli valence on sort of reduction in emotion in response to sort of restriction and things like that, right? So my question is, I'm interested, do we see greater reductions in normal expressive behavior when people are expressed to sad stimuli or sad events, or do we see greater reductions in expressive behavior when people are restricted in response to humorous stimuli? Okay. If that's the question, which of these comparisons are the most important to make? What's that?
The ones on the right.
One's on the right? So if I'm expressing, do I see more greater reductions in sad versus humor, or if I'm withholding sad versus humor, right? This kind of says, stimuli, expression, this is saying, what's the impact of not regression, restriction, or regulation, that's what I was thinking, regulation on the stimuli here. Here, we're saying, here we're looking at the impact of sort of regulation on expressive behavior being impacted by these ones.
I think I was just looking at the
No.
sad versus humor, and that's like.
Yeah, and sort of making sure that you're clear on this, right? I would make an argument that I'm kind of more interested in this one. sort of, does the type of emotional sort of situation that I'm in, does this impact sort of the level of reduction in my expressive behavior, right? So across situations where I'm asked to express or withhold, right? Express or withhold, do I get greater reductions when I'm feeling sad or when I'm feeling sort of kind of happy? Okay. We'll kind of see how this is going out.
I thought that was, it wasn't, I didn't realize it was a rhetorical question.
Okay, so, and now if I go through and I switch this around, this is kind of a different question. Like, it's easier for me if I'm looking at this, these are the comparisons with the groupings, these are the comparisons I'm making, right? But here it's saying, if I express my behavior, if I'm just naturally expressing emotion, do I demonstrate more expressive behavior in response to sad versus happy films? I don't know that I care about that so much. It's not really an interesting question to me. Or when I withhold my emotion, do I demonstrate more expressive behavior in response to sad versus happy stimuli? That's kind of relevant maybe. But based on this question, I'm probably going to be more interested in, do the effects of emotion regulation differ across different emotional situations, right? Do I see, does this emotionally valent situation I find myself in, does that have an influence on the degree at which I'm able to restrict my emotion if I'm trying to do that, right? And so this is what this is what I would argue would maybe be the better way to go through. Now we could go through and look at all possible comparisons, but if we're doing that, we're running a lot of tests, we might want to start thinking about, do we have to sort of impose control or things along those lines. So this is why this is why graphing it starts to become important. I can say, okay, these comparisons and these comparisons are kind of interesting. These are comparisons that we could do, but I don't know that tells me a whole lot of something that's interesting, right? So when you're doing this, always want to say, what's my research question? And if I'm going to put forth effort into this, what are the questions, what are the comparisons that are maximizing sort of the things that I'm interested in? Okay. Questions about this, the thought process that we've gone into this. Okay, so we decided that we want to look at the difference between expression and withhold separately in people who watch the sadness film and for people who watch the humor film. Okay, how do we go through about doing this in SPSS? What's that? T-test, perfect. Yep, we're going to do a T-test. How do we set this up in SPSS? How could we do this? So we want to run a T-test comparing express versus withhold separately in people who watch the sadness film and people who watch the humor film.
Independent.
Okay, yeah, independent sample T-test. How do we get SPSS to do this separately for people who watch the sad film and people who watch the humor film? Split file, right? So what we can do, if we go and we go to analyze, or excuse me, go to data split file, and we want to look at the comparison of express and withhold separately across sadness film and humor film. So what we're going to do is we're going to compare groups, and we're going to say film condition, this is what we're splitting the film up, or the setup by. You guys hit paste, I'm going to hit OK. And then if we take a look at our set, we'll see that the SPSS has split this into people who watch the sad film and people who watch the humorous film. Okay. Now what do? Everything tomorrow? You're on a roll.
Analyze.
Yeah. What am I going to request from SPSS? Yeah, an independent sample t-test. Right? Go to independent sample t-test. Outcome is my expression rating. I am going to want to look at film condition. That's 0, 1. Continue. You guys hit paste. I'm going to hit OK. So we go down through and take a look. We see that SPSS here has provided us with t-tests for, I guess I broke it up a little bit different in the handout, but what we've got is we've got a t-test comparing express versus withhold for people who watched the sadness film, and express versus withhold for people who watched the amusement film. Okay, so if we're going down through and we're taking a look, Chrissy, for people who were randomized to view the sadness film, do we see a difference? Do we have evidence supporting a difference in expressive behavior across express withhold for people who were watching the sadness film?
We do have some evidence.
Yeah, and tell me what the upper and lower bound estimates of our confidence interval is for
For the difference?
For the difference, yeah.
So 0.147 and 0.859.
I tricked you.
Oh, because we're not assuming.
There we go, yeah. So-
0.152 and 0.854.
Okay, cool. So if we look at our Levine's test, right? For individuals who were watching that sad film, it looks like we have a violation of homogeneity of variance for people who were watching or who were instructed to naturally watch versus those who were instructed to inhibit, right? And so because of that, we're going to drop down to equal variance is not assumed. It doesn't make a huge practical difference, but it's going to be the more appropriate test to go through and make, right? And so we see that for people who are watching the sad film, we go through and we see point estimate, we see a 0.503 unit difference, right? This is a 1 to 5 scale. It's a reasonable amount, right? Half a unit decrease. And our confidence interval around this is going to be 0.152, 0.854. Okay. And what about for humor? What are we seeing here? Silent?
You're seeing 1.018.
Okay. So point estimate of our difference is 1 point.
1.02.
What's that?
1.02.
Yeah, 1.02. We'll keep it 3 decimals just to keep it consistent here. But yeah, you round that down, that would be fine. And what's the confidence interval around that?
0.605 and then 1.431.
Okay, is that right? Do we have a violation of homogeneity variance there?
No.
Okay. So what's our confidence bound going to be?
It'll be 0.606,
There we go.
1.429.
Okay, perfect. And if I go through and I pull out my effect size calculator to go through and take a look at this, right? What I'll get is for my sadness group, I get an effect size of 0.597 with bounds running from 1.75 to 1.020. And G for my humor is going to be 0.995, or about 0.57 and 1.411. Okay. So what, going back to our effects here, how do we make sense of this? How do we interpret what's going on? CJ, do you have an idea?
Looks like there's a bigger effect for expression withholding during the humor film.
How strong is that evidence of greater, of a larger impact of regulation for humor versus express, or humor versus sadness. Is this compelling evidence? No? Yeah, what do you think?
It's a pretty sizable effect.
Pretty sizable effect, right? And so if we look at the difference, the point estimate of the difference, right? We see that it's for the humor film, our point estimate of the difference is about double what it is, right? If we're looking at the effect size, it's not quite double, but it's a noticeably larger effect for one versus the other, right? What about if we look at those confidence intervals around those point estimates? What do you think, Chris?
I'd say it's pretty inconclusive because there's plausible values that include that go on with what we were just saying, that humor seems to have higher expression than sadness, but there's also plausible values that say the reverse.
Yeah. See, and so this is why I really like this SKI tool in terms of trying to think about what are our data really saying, right? So I can go through and I can say for my sadness film, I can say the point estimate of the difference is 0.503 with a lower bound of 0.152 and upper bound of 0.854. And then for my amusement or my humor film, point estimate of 1.018, lower 0.606, 1.429. Okay. And so if I look at those, so this is my point estimate. Here and here, right? We've got about over a half point difference across these two. But if I look at my intervals here, and think back to coming in vintage, right? Does this look like something that looks like it's sort of a compelling difference across the overlap of those two intervals? Probably not. Okay, and this is consistent with when we go through and we take a look at our interaction. Our interaction, it looks like there's might be something there, but again, inconclusive, right? We're not seeing strong evidence that the impact of regulation on expressive behavior is very clearly dependent on the type of stimuli people were presented with, right? And so this is often what happens. It looks like, yeah, kind of, right? And if we go through and we look at yeah, it looks like this is bigger than what's going on here, right? And if we drew lines, these wouldn't be parallel lines. And the question is do we have strong evidence here that we have a dependency between my film and my instruction condition? And really, it doesn't look like it, right? And so we would say sort of our follow-up tests here are generally inconclusive or kind of ambiguous or don't provide strong evidence for things along those lines. We really very clearly are getting reductions in expressive behavior when we tell people to inhibit their expression relative to just letting them sort of express naturally, right? But we don't have super strong evidence that the magnitude of that reduction is dependent on whether or not people are exposed to humorous stimuli or sad stimuli, right? And so again, if we go back to our ANOVAs test and take a look at our instruction by film interaction, right? We get a p-value of 0.063 and an S of 4, a base factor of 2, right? It's, I don't know, it's not nothing, but it's not hugely compelling evidence either, right? Other thing too, we have a pretty large sample size, right? We've got a cell size of about 45 to 50 or so. It's not something I say, well, it's sort of hugely, well, it is underpowered, but it's not massively, like I've got cell sizes of 6 and 7 or something along those lines, right? So I guess what we can say for sure, based on these data, and I think fairly, make a fairly strong argument that yes, whether or not we're having people watch humorous films or sadness films, that has an impact on expressive behavior. And yes, if we tell people to regulate or down-regulate their expression, they are able to do that effectively. We're seeing meaningful reductions in expressive behavior, right? But the extent to which people's ability to regulate expression depends on what type of emotional setting they're in. That's still kind of an open question, right? Certainly wouldn't say that there's not an effect, but certainly not strong evidence saying that that this is something that we can follow up with. Okay. How are people feeling with this? Who's confused? No one's confused?
That's a quick question.
Yeah.
So, is there a reason we use psi for the point estimate?
Oh, it's just sort of, it's value of contrast.
Oh.
I mean, and so, yeah, it's just short term, so, because I don't know, I like that better. I could use change, but then that looks like the glasses delta makeup or something like that.
Okay.
So I'm just using contrast notation there. Questions? Okay, so this is a 2x2, and this is actually not too bad. And if we were to go through and take a look at the other, flip this around, because you might, and there's going to be times when you run an interaction, and then you look at it like this, and you don't find an effect here, and it looks all kind of the same. It's actually the interaction is being impacted sort of by those comparisons. Here, you get basically the same thing if you flip it around, just continues to be inconclusive. But again, based on that, on this interaction effect is saying that there's just not a lot of there's not strong compelling evidence that the impact of regulation changes across emotional stimuli here. Okay. All right, so let's go through and work on something that's maybe a little bit more clear cut. So go ahead and open up and grab your handouts for the trauma beliefs data set. And again, just to kind of give us a headspace to work from, we'll say, work through this, okay? So we'll say that existing research suggests that people's belief about enduring impact of trauma exposure can be classified in 1 of 3 profiles. Respondents in our benevolent profile in this set report relatively positive perceptions of post-trauma outcomes. That people with serious trauma are generally the same people they were before, so things along those lines. People in the negative profile, these individuals are endorsing negative, potentially pejorative beliefs. People exposed to serious trauma are damaged. They're violent, and so on and so forth. And then we've got a last profile, kind of intermediate, generally sort of positive stuff, but what people are tending to do is endorse specific concerns regarding sort of interpersonal relationships with people exposed to serious trauma. So I would be hesitant to develop a romantic relationship with someone who's experienced similar serious trauma. So we've got 3 different folks, groups. We've got a benevolent group, a negative group, and then kind of a sort of an in-between group that seems to be okay for the most part, except for when it comes to would I have someone exposed to serious trauma to watch my kids? And I don't know about that, right? And so what we're interested right now in this project is the unique and interactive effects of belief profile and respondent sex on trait level positive and negative affect. Okay? And now we're going to come up with some specific hypotheses here. We're going to say that with respect to positive effect, folks in our benevolent profile are expected to score higher than the combination of people in the negative interpersonal profiles. So for positive, right, we're saying that benevolent can have greater levels of positive affect than our negative and our interpersonal. We could report similar levels of PA. So we're going to say, and positive affect. And for negative affect, we're saying that people in the negative profile will report higher levels than the combination of benevolent and interpersonal. So we got neg greater than benevolent plus interpersonal. And then based on previous research, we're expecting women in our sample to report higher levels of trait negative affect relative to men. So we say men. Okay, so these are our predictions, and then we say interactive effects of profile and participant sex are considered exploratory within these data. Okay. And so if we pick up, take a look at our handout here that you've got. We've got participant number, sex, male, female, PANAS pause, PANAS negative, and then class interpersonal beliefs and negative here. Okay. All right. So we're not going to go through and run a screening on these data, but there's some stuff going on in these data that's important to see. For the most part, the stuff that I've thrown at you guys at this point in terms of screening, like, oh, the design is unbalanced and there's not, distributions aren't perfect, but for the most part, it's like, it's pretty good, it's fine, right? With these data, there's actually stuff that comes up, okay? So if we go through and we were to take a look at histograms for our positive affect and our negative affect. Here, again, what I've done here, this is STATA, but have gone through and coded. So we've got, this is a 2x3 ANOVA, right? We've got sex by profile, 2 levels of sex, 3 levels of profile. So we've got 2x3, we've got 6 individual cells, right? So we've got, for our women, we've got interpersonal benevolent negative. For our men, interpersonal benevolent negative. And this is our graphs for positive affect, okay? Sally, what are your thoughts and impressions about this set of graphs?
Distribution's fairly normal.
Yeah, distribution is fairly normal, right? If we go through and we take a look, we've got some degree of unequal cells. If we look at our lowest number is going to be male interpersonal. So that's got 28 people in it. Female interpersonal, it's 110. So we've got a considerably unbalanced design, right? But if we go through and we take a look, not too concerned about those distributions. Okay. Nick, what about these folks over here?
Looks like there's some positive skew.
Yeah, we've got some positive skew, and yeah, we've got some positive skew, and we've got a whole bunch of kurtosis. Like kurtosis are like 10 and stuff like that, which is kind of nuts. Okay, and we're also seeing some outliers going on out here, and all of a sudden this starts to become problematic. This, I may make an argument with 110 people, I kind of get away with, right? Are we concerned, is the normal distribution of our observed scores, is that an assumption of our ANOVA model? No, why not? What is the assumption, Chris?
I don't exactly remember, but I remember that the F distribution isn't normal. Is that right? Does that have something to do with that?
No, not the F distribution. So if we're looking at our observed data, what's technically the assumption of our means-based analyses? Is it the observed data, the distribution of the observed data?
Oh, the population.
Well, not quite the population.
The
Distribution of sample means, right? And Nick, under what two conditions are distribution of sample means start to become normal?
The population's normal.
Population's normal.
Sample size approaches.
Sample size is sort of getting bigger, right? And so here, for this, if this was the only graph that I had, I might be able to tolerate that. I'd say 110 people, that's not normal, but these folks are probably not going to impact that too much with that size of cell. And the sampling distribution of this distribution, even if this is representative population distribution, that sampling distribution is very quickly going to become normal just because we're sampling at sample sizes of 110, right? Down here we got 28, right? That's problematic. This guy with a sample of 28, that's going to start dragging means around, right? And so I start to become concerned with this, right? If I go down through and I take a look at box plots, right? So again, this is, I didn't clean this up too well, but we've got interpersonal benevolent negative, interpersonal benevolent negative for men and women, or women and men. Same thing here. Alicia, how does that look?
Pretty good.
Pretty good. Not too concerned about this. What about these folks over here? Yeah, that looks bad, right? If we go through and we take a look and follow up with z-scores and look at extreme values, each one of these points are all going to be points that are in excess of 3 standard deviations, 3.5 standard, they quite a bit in excess of 3 standard deviations. These are points that are going to be in excess of 4 standard deviations, right? Again, this is a pretty big sample, so I'm maybe less concerned about this. But over here with the men, we just don't have a lot of men in the sample. Now all of a sudden we start dragging our means around. Oh, these are way out here, right? And so we're having concerns. This would be a situation where it would probably be hard to make a strong argument for, oh, I'm not even going to explore some way to correct this. I'm just going to go ahead and just hope for the best and assume things are going to be okay, right? We also have no violation of homogeneity variance here, but obvious violations of homogeneity variance here, right? So we've got unbalanced cells, we've got violation of homogeneity variance, we have evidence of extreme values. The only thing that's kind of going for us is that the skew is all kind of pointing in the same way, but still starts to become hard to make a strong argument that, oh, this is going to be fine, I can just move forward with the data as planned, right? So again, in this set, 34 missing values, that's not a problem. There's just like people who we don't have. There's no systematic stuff going on. And for a PANIS positive, we've got unbalanced design, so minimum cell number 28, 110, that's a big discrepancy, right? But otherwise, everything's looking acceptable. For our negative, PANIS negative, we've got an unbalanced design, notable deviations from normality, particularly in our smaller samples. Extreme values, evidence of non-constant variance across our individual subpopulations. There's just a lot of stuff, right? This is probably too much to just ignore and move forward with without looking at other options. And so move forward for a PANIS positive would say, sure, go nuts, move forward. PANIS negative, probably need to look at different types of transformations, okay? And this starts to become important. And particularly like for Nick, if you're doing substance use stuff, a lot of the outcome variables and the use variables, I would imagine, tend to have a strong skew within your literature, right? And for you, if you just go ahead and sort of proceed with like audit scores or something like that, and you don't have some sort of transform, you're probably going to get in trouble for that because people are going to say, hey, these are skewed data, there's problematic stuff with this, we need to go through and transform. We haven't talked about transforms a whole lot in this class. We'll talk about it more next semester. I'm historically have not been excited about transforming data, but I'm starting to come around. Big issue with transforming data, as soon as you transform a variable, you're no longer working with the variable. You're working with the transform variable. The transform variable doesn't have the same interpretive value as the untransformed variable, right? If you ask me what the natural log of BDI score is, I don't know, right? But that's what I'm using. And if I log transform BDI, I need to make it very clear throughout my writing and my interpretations that I'm not working with BDI, I'm working with a log transform of BDI, right? And so what we do is we lose a tremendous amount of interpretive value, and we'll see this, we won't, but it did. We'll see that this starts to lose our ability to make some of the practical interpretations that we've had. So this is always wanting a way. You don't want to transform unless you have a good reason to transform. Some people just jump off and there I go. My skew wasn't 0, so I transformed the shit out of stuff. You just lose all sorts of interpretive qualities with this, right? But in some cases, when your data look like this, is not going to be responsible to just charge ahead without at least exploring some other options. Okay? So if we go through and we do that, right? So you can't, I don't know if you can see this real well, but so this is a couple of different transforms. I tried 2 different transforms with these data. One is a natural log transform. Natural log transform has a lot of positive qualities to it. It retains a lot of interpretive value. Natural log transforms are very nice, but sometimes they don't always sort of do the trick. And so we have other types of transforms that do sort of a better job of addressing more extreme versions of skew. And so this is a natural log transform. This is an inverse transform. This is taking the variable and taking the 1 divided by the variable. So we're just our natural log transform is just a natural log of x. Our inverse transform is going to be 1 over x. Okay? And that 1 over x does a very good job of addressing some pretty significant skew. So if we go through and take, now this is theta. Skew is skew. It's calculated a little bit different. But if we look at skew for our natural log variables, we still have some cells here. Our male benevolent still has skew getting close to 2, right? Here we have, for kurtosis values, you just subtract 3. So for our male benevolent, we still have a skew of close to 2 and a kurtosis of 3.66. That's still not great in terms of stuff, right? I mean, we don't have a tiny cell, but it's still not super great here. But here's our inverse transform, okay? Here we look at our skew values. Our skew values are all looking pretty good. Our kurtosis values, again, remember you subtract 3 from this. So our one cell that we still maybe had some concerns with our natural log transform, we now have a skew value of negative 1.15, or kurtosis value of 0.78, right? So it looks like our inverse transform is doing a little bit better job of sort of redistributing this into something that looks a little bit better. We go through and we take a look at our histograms, okay? This is our natural log transform. So it's better than what it looked like before, but it's still, particularly out here, it's improved it, but we could still say that it's still lacking to some extent. But if we look at our inverse transform, tomorrow, how are you feeling about that inverse transform? Better than before, right? Do you know, is there anything that you notice about sort of these graphs relative to these graphs? Yeah.
It's a positive skew, it's negative skew.
Yeah, what's going on there?
Because the transformation of it.
This is another thing you need to be aware of. What we've done with that inverse transform, it flips things around. High is low and low is high now, right? If I take 1 divided by 5 versus 1 divided by 50, which is the bigger score? 50. That now becomes a much, much smaller score. So also, when we're going through a transforming, if we do something that goes through and flips this around, you have to be aware that larger scores now represent smaller values of negative affect. Smaller values now represent larger values of negative affect. You have to make sure that you split that all around so that your interpretations are correct. Okay? Same thing if we go through and take a look at our box plots. Our natural log is doing all right. There's probably, we could get away with this, but our negative or our inverse transform is doing a much better job. But we're seeing that this skew is now going the opposite direction as the other one, right? Which is fine. We just need to make sure that we include that in our interpretations. Okay. Questions about this? Yeah.
I guess when doing these transformations, what's the consensus, or if there's one like debate around balancing like a reasonable transformation versus one that gives you more, I guess, meaning in your interpretation in terms of like flipping skew?
Yep. So think about how do we choose transforms and so what makes the most sense? Do we transform, do we not transform? This is all sort of based on stuff that you have to kind of go through and figure out on your own. Oftentimes, if you're in the literature, you might substance use, alcohol substance use stuff, I've had friends in that area, and it's just common knowledge, we just transform. Like this is just the transform that everybody uses, and it's gotten to a point where that transform variable actually holds meaning just because we've used it a lot enough so that within my field, I kind of know what a log transform and an audit score is and what constitutes a large value or not, right? Same thing if people do any type of experimental like reaction time data. Reaction time data notoriously skewed. So most of the time we're sort of pretty quick, but then we have latencies, right? And so we see that tail out. I can't have negative reaction time, but I can have exceedingly long reaction times, right? And so if you tried to publish non-transformed reaction time data, you probably get told that you need to figure out what's going on in this literature, right? But for a lot of times we just run this stuff and it's like, okay, well, yikes. Within this, for this scale or within this population, it looks like these data aren't optimal for the design that or for the analysis that I want to use. So thinking about weighing out the pros and cons, okay? Now in these data, when I go through and actually run it, it does make a difference in terms of the types of effects that come up, right? Sometimes, a lot of times, if I go through and I run my transform data, and then I run my untransformed data, if it doesn't make any practical impact on the actual outcome in my interpretations, the effects that still pop up are still the effects that pop up whether they're transformed or not. I'd probably make an argument, well then just run your non-transformed data. Note in the paper somewhere that, hey, we noticed violations of normality within these data, explored transforms, results were functionally identical, therefore we presented analysis in untransformed data facilitate interpretation. That's fine. But if I go through and once I account for violations of my assumptions, and all of a sudden some of those effects that I really liked disappeared and are no longer there, that starts to question whether or not those were real effects anywhere, just as a byproduct of just having massive violations of my underlying assumptions. And under that situation, transform data is probably better. But recognizing that it's not a free lunch. Now, describing what's actually going on starts to become kind of more of a process because we need to make sure that people understand that we're using transform data, and that's a different metric than some of the other stuff. And then sometimes what happens with, so if I take within this inverse transform, right? If I go through and I say, so the mean for study 1 is 0.006, and the mean in group 2 is 0.010, right? I can go through and take those means and inverse those, 0.01. So that would be a score of 100. And that's going to be 166.66. Okay, something like that, right? I can go through and now and backtrack. Now those scores don't make sense given the scaling of Panis, but whatever, right? And so that's fine to do, okay? So I can go through and back transform. But if I take 0.010 minus 0.006, I get 0.004, right? So that's saying that the difference between my transform variable is 0.004. If I take 0.004 and inverse that, that's a value of 250, right? If I subtract this from that, is that 250? Nope. Now all of a sudden I've got a difference, a subtraction from a transform score that doesn't have any practical meaning. I can't back translate that into something that makes sense within my common metric. And now all of a sudden it starts to get hard. It starts to become hard for me to say, is this a meaningful effect? I can go through, I can still calculate a standardized effect and effect size and say, I can say, so it looks like that this is associated with a large effect, medium effect, a 2 standard deviation, or yeah, 2 standard deviation, like 0.8 of a standard deviation increase from this group to that group. But if I want to go through and take a look at the actual sort of the Trump scores, okay? So this is all stuff that you have to think about that we don't think about often. People just go ahead and throw on a transform and then just pretend like they didn't. and run through the rest of the study and not report that ever. You're using a completely different scale, a completely different metric, and so you have to be careful in terms of how you're thinking about it and interpreting that. Make some sense? Okay, cool. Let's go through, take a break. I'll leave you with some more expressive behavior. Chris saw the Dave Matthews poster hanging out in my office. So.
What? That's awesome.
Hanging out, and me and Tim Kaine and Dave Matthews. Tim Kaine kept trying to talk to me. I'm like, get out of here, dude. I'm just to talk with you right now. For unique and interactive effects of sex and profile on positive and negative affect, right? So even though we said we need to transform these data, we're not going to transform the data, we're just going to let the data the way they are, but you would want to transform these data before you were really going to go through and take a look at them, but we won't, because I would have had to change everything around. So we go to general linear model, univariate, right? And we're going to look at first positive affect. And we're going to go down through in our fixed factors, we're going to look at class, we're going to look at gender, we can go down to options, we're going to request descriptive statistics, homogeneity test, estimates of effect size, continue, we'll ask for marginal means for gender, class, and our interaction, just because just a nice kind of quick snapshot. When we're looking and comparing things, we'll probably use our observed means, but we'll just request marginal, just because it's kind of easy to go through and do here. And all right, so you guys hit paste, I'll hit OK.
Wait, so what do you do the display name for again?
Display means it's not super important. So EM means gender, class, and it's just giving you a breakdown. The descriptions will give you the stuff that you need, but it's nice sometimes to just have those to eyeball real quick. So, looking at our outcome here, okay? So notice, as we talked about in our screen, so if we're looking at our individual cells, we've got anywhere from a low of 28 to a high of 110, so we've got hugely unbalanced design here, but our descriptive statistics are our factors here. Taking a look at, though, for our Levine's test for positive affect, we don't have evidence of violation of homogeneity variance, so feeling pretty good about this. If I go down and take a look at my effects table, Alicia, what am I seeing in my effects table here? Yeah, nothing worth talking about, right? So based on these data, it looks like we do not have, basically the data that we've observed looks fairly compatible with the null hypothesis of equal levels of positive affect across men and women. And also these data look compatible with our null hypothesis of equal levels of positive affect across our individual profiles. We see really no compelling evidence of any type of dependency of sex and class status, at least in terms of positive effect. So do we have anything really to talk about in terms of PA stuff? Not really, right? And this is where we can start to, I mean, if we take a look at our box plots here, right? Now these are medians and not means, right? Through the median-based statistics, but it looks like things are all kind of in the same general area in terms of stuff, right? So if we were looking carefully at our during our screening, we might not be super surprised by this. Okay, so looks like positive affect is a wash. So let's go down through and go and take a look at negative affect. So we're going to go down to general linear model, univariate, and we'll just swap out negative, positive affect. drop-in negative affect. Okay. You guys go ahead and hit paste. I'll hit OK. Now we got sort of a little, we got a little bit different thing going on here. Now we have Levine's test is telling us what, Chris?
Whether there's violations of homogeneity.
Right. And do we have a violation of homogeneity variance?
No. Yes.
Yeah.
Sorry.
And what's telling you that, yeah, we likely do?
There are significant p-values based on means.
Right. So our p-value for negative effect based on the mean point 0.005. And what's important to recognize, and so Alicia stated that you're, in order to run this in Stata, what we're doing is you're taking that cell variable, and so creating, like we did in our screening, right? So we have an individual, we have a categorical variable that has a label for each one of our individual cells. Now this is a 2x4, so how many cells do we have, or excuse me, a 2x3, how many cells do we have in this set? 6, right? And so what this is saying, that across those 6 cells, that based on these data, we have evidence that the population variances for each one of these individual subpopulations is likely not equal based on this, right? Now in Stata, what you do is you create that cell variable that you need to do for your screening, and then just row var with your individual cells, and it's doing this. SPSS just kind of does it all on its own for you there, right? Well, essentially what it's saying, like, well, because we've got main effects, we've got a main effect of A, main effect of B, and the interaction. What's not equal? Well, somewhere across those, the within subjects, the within group variability across those individual cells, at least one of those cells has greater levels of variability than at least some other ones, so there's stuff going on there, okay? Now, what SPSS does is it says, yep, you have a violation, and then proceeds to drop down and give you tests as if there were no violation here. And this is the problem. So I need to go through and take a look. It looks like New Edition has added in some additional things, right? And we're going to go through, depending on this, do some follow-up tests. But right now, I don't have confidence in the validity of these omnibus tests, given the violation of homogeneity variance, the unequal, the unbalanced design, all the stuff that we saw in terms of the distributions and things along those lines, right? And so there are some concerns about how good these are. And when we go through, if we actually rerun this with inverse Panis negative, this effective class goes away, suggesting that we probably shouldn't put too much faith in this stuff, right? You can always, if you have concerns, run things with the transform, run it without, see if it makes a difference, right? When we get into the regression stuff, when you have weird outliers, run it with the outlier, run it without. If you drop 2 or 3 cases because they're outliers and it completely changes the effects that you're getting in the paper, that's 2 or 3 people shouldn't have a massive impact on the effects that you're getting in any type of analyses, right? So important things to think about. But if we're taking this at face value, we're saying, okay, well, ignore this, and we're saying, I guess tomorrow, what are we saying based on our, if we're accepting these as reasonably valid, which is probably not, shouldn't, but if we were, what do we got going on here?
Yeah, we have the main effect of gender and class, but no interaction.
Right, so we have a main effect of gender, we have a main effect of class. Can we interpret these main effects just looking at the page right now? None of them?
Well, gender.
Yeah, okay. So what is, tell me how you're interpreting the main effect of gender here.
It looks like females are achieving higher scores for negative affect compared to males.
Okay, cool. And so this is kind of what we had in our prediction, right? So what we could just leave it at that, right? Now, what I might want to do is then go through and just run a t-test comparing men and women on negative affect, because then it's going to give me, well, or I could just pull up my calculator and just run an effect size there, run a means-based comparison, right? So calculate a hedges G, maybe the confidence interval around that if I wanted to. I could also, if I just ran this as a t-test, it would also just automatically calculate my confidence interval for me real quick, right? And that would be nice. So if I just go up and I don't want to mess with it, doing it by hand, I can just go up to compare means, independent sample t-test, and look at, I have those 0, 1, is that right?
Yep.
Yep. 0, 1, and you get negative affect there. Okay, so and then that just does, I mean, this F test up here is sufficient to tell me that I do have a main effective gender. The men and women differ in terms of their negative affect, the reported negative affect scores. I can look at my partial eta squared and say that participant sex accounts for about 2% of the residual variability, the residual variability in negative affect, controlling for class and the gender by class interaction. That who hears that interpretation of that partial eta squared and is like, oh yeah, I know exactly what's going on. Probably right. And this is why, so that means-based comparison, if we're doing a means-based test, that means-based effect starts to sort of be more meaningful. So if I just go down through and run this, I see that I don't have a violation of homogeneity of variance across men and women. And so I can go through and say, okay, it looks like based on these data, women are scoring about 1.5 points higher on the PANIS relative to men, with a lower bound estimate of 0.1 and an upper bound estimate of 2, right? Now PANIS scores range from 1 to 50. So these data are saying that at most we have not quite a 3-point difference in terms of negative affect across men and women. Do we have evidence for a non-zero difference based on these data? Some, right? I mean, our p-value, okay, so I'm going to go through, I'm going to double click this. Oops. We got a p-value here. Drop that in my, so I've got an S value. An S value of 5, a base factor of 3.2, right? Is this something that I would say is conclusive evidence for a gender difference across men and women? Probably not, right? I mean, some, right? But again, thinking about benchmarks for base factor, anything from 1 to 3.2 is weak evidence. 3.2 to 10 is substantial, right? So we're just kind of on the low end of stuff. So yeah, we have some evidence that there's perhaps a difference in terms of negative affect across men and women. But does it look like this is a meaningful, something that, a difference that has some sort of practical meaning to it? Yeah, what makes you say likely not, Chris?
That there's not a likely meaningful difference.
Yeah.
Just everything's pretty much on the borderline.
Right.
Of being.
And if I think it's sort of these data at the low end, these data are consistent with a 1/10 of a point difference across men and women in the population. Is that something that is incredibly compelling in terms of a difference in a scale that ranges from 0 to 50?
No,
Probably not, right? And even at the high end, it's looking like it, at most, like not quite a 3-point difference. It suggests, yeah, maybe the difference isn't 0, but the extent to which this is a practical or meaningful difference starts to fall into question, right? If we take a look at how many people we have in this, how many men and how many women we have in this sample. 105, 228. Are we worried that this is like a small? No, I mean, we've got a pretty good lead on means-based stuff, right? And so, yeah, we would say these data provide some evidence for perhaps a non-zero difference in negative affect across men and women. However, the lower bound estimate at confidence interval suggests, and even the upper bound says like at most, these data would support a population difference of less than 3 points on the PANIS difference across men and women. It's hard to make a strong argument that that's something that's clinically and practically meaningful in terms of stuff, right? So in terms of sort of thinking about this, if we go through and pull up our effect size calculator, we got 15.841, 14.351, standard deviation 5.959, .89, and then we got 228 and 105. So we got an effect size of about 0.25, right? So something that's consistent with a small effect going on here, right? And then if we wanted to, we could take that T and calculate the upper and lower bound and sort of go through and talk about this. So, but this is important, right? Because yes, we have found evidence in support of a sex difference in terms of reported negative affect, but is this something that's, what's the magnitude of this effect? Is this something that's going to be sort of something that we're likely to notice a difference out just sort of in the general population? Probably not, right? So it's not to downplay this, or this could have important implications for theory or things along those lines, but wanting to contextualize the strength of evidence for this, okay? So we've gone through, explored that difference in terms of gender. What about class, CJ? What's going on with class?
There's also conventional benchmarks of significance for class.
Okay, yeah, right. So we can say we also, in addition to our effect for gender, we're also seeing maybe some evidence for differences across our individual belief profiles in terms of negative affect. Okay. Do you have strong evidence for that? Not really. I mean, it's okay evidence. It's some, right? But it's maybe worth going through, particularly if we call this, if we predicted this, worth going through and investigating a little bit more. Now, tomorrow, can I make an interpretation of class differences in terms of negative affect based on this, on this stuff?
No.
Why not?
Because we have three.
Because we have 3 different ones, right? So how do we go about evaluating or looking at differences across those three different levels of class? What's that?
One-way ANOVA.
Oh, I could hug you. Absolutely. Why?
Because we need to partition the variability since there's 3 levels to figure out how it's different.
Exactly, right? So we've got here 2 main effects, no interaction, right? The one main effect only has 2 levels, so that makes it kind of easy to go through and interpret. This is something to think about when you're designing studies. If 2 levels will work, and 3 levels you could do, but so maybe the question is like, is this really worth it? Stick with 2. 2 is going to make your life a lot easier, right? But in this case, we had evidence of 3 different profiles, and so we needed 3, so we went through and took a look at that. So what we and take a look at through a one-way ANOVA to start to tease these apart. okay? Now remember that we also had a specific prediction about this, right? Remember that for negative payments, we had expected our negative group to have greater levels than benevolent and interpersonal, okay? This is what we called on the front end. So what would be a good idea to do as we're requesting that ANOVA model?
Linear contrast.
Yeah, want to set up a linear contrast, right? And SPSS will do this for us, so this helps us not have to crank out a bunch of statistics by hand, which is nice, right? So if we go down to compare means, one-way ANOVA. Factor is going to be class, our dependent is going to be negative affect, and then we're going to go up to contrasts, right? And what are the contrasts that I'm going to set up for this? What's my first weight going to be? Negative 0.5. Yeah, why is that negative 0.5?
Because we're not looking at the interpersonal consistencies or
You're right, it is negative 0.5. Why is it negative 0.5?
it's because we're assuming that there's going to be more effective negative.
Okay, right, so we put the negative on there, right? Why are you, Sally, why are you giving a weight of 0.5? You're right. Why would we weight that 0.5? Someone have a problem? Mark?
Because we're combining benevolent and interpersonal together.
Perfect, yep. We're combining the benevolent and interpersonal. And so we see we've coded interpersonal concerns as our first code, so we get to -5. Benevolent is our second code, so what's the code there? Negative 0.5. And what's our code, our last code? 1. Okay, so again, we see we're comparing these two groups versus this one, right? So take 2, inverse of that is 1/2, so negative 0.5, negative 0.5. So we go through and we set up this contrast. And so we're just looking at 1, so we can set that up in SPSS. So we're going to go negative 0.5, negative 0.5, and 1. Continue there. There's the options. We'll ask for descriptives, homogeneity variance or Welch test. Now we saw that when we ran our omnibus test that we had violations of homogeneity variance, so we want to go through and probably sort of take a look at that. Now really, we can go through and probably should do this just so that we know what's going on in our data. But are we super interested in the omnibus results of this one-way ANOVA? No, why not, Kristen?
Because we've already, to some degree or another,
Yeah, we've already done this, right? The only reason we're requesting an omnibus effect for this is because we have to, in order for SPSS to give us the contrast, which is actually what we want to look at in the first place, right? So we're going to go through and do this just so we kind of know what's going on, but we're not interested in this. We've already got our main effect that we know. Now, is it possible that this main effect that we found within the context of the Factorial ANOVA doesn't actually turn up as statistically significant in the one way? Yeah, why is that, tomorrow? What do we talk about in terms of the power of our factorial designs relative to our one-way designs?
It
Has more power. Why is that? What's that?
The error term.
The error term. What have it? On average, all things being held constant, what do we expect in terms of the error term to be in our factorial design relative to our one-way design? Smaller, right? So we've had in these data, so that we know in terms of negative affect, we know that participant sex does hold a relation with negative affect, right? And so in our factorial design, we've modeled the variability that's attributable to sex as an actual effect, right? And if it's modeled as an actual effect, all the variability that's attributable to sex Does that get to go in the error term? Nope, it's pulled out of the error term. What about for our one-way? Have we modeled sex in our one-way? So all that variability in our outcome that goes towards sex, where does that go? Straight into your error term, right? So be aware that just because I get a significant main effect in my ANOVAs test, it may not, particularly if it's kind of right on the edge, it might not come up in your one-way, but we don't care about it. From the standpoint of this test, because we already have evidence of a main effect, all we're using, we're just hijacking SPSS to have it calculate that contrast for us, so we don't have to crank it out by hand. Okay? So, if we go through and we hit continue here, you guys hit paste, I'll hit OK. And so as we go down and we see, yeah, we still have, okay. So when we're looking, it looks like we do still have a violation of homogeneity variance when we're just looking at differences across different profiles. So that's going to be relevant. Now, our one-way ANOVA says that, yeah, we still have some evidence of different mean negative affect across our different profiles. We're not too concerned about that. Although what happens to our, CJ, what happens to our ANOVAs test once we account for violations of homogeneity variance? In terms of the output here.
Once you account for it, decrease. Or
So if we see that we have a violation of homogeneity variance, are we looking at our ANOVA table in terms of the ANOVAs effect? Yeah, what are we looking at?
Welch,
Yeah, what's our p-value for that Welch's test?
higher.
Yeah, right. And so this you start to see the impact. Like we shouldn't just be ignoring violations. Now, sometimes when we ignore violations and then we account for them, our effects go away, or sort of evidence for them starts to reduce. But sometimes the opposite happens. Once we account for that stuff that was masked or swamped before, it actually starts to come up. So it's an important thing to go through and take a look at. So again, speaking to the fact that this is an issue. Okay. So when we go through and take a look, we want to go down through. Really, none of this above is anything that we're interested in. It's just something we're kind of eyeballing out of curiosity. But if we go down to my contrasts, I'm seeing that, okay, interpersonal, -5, benevolent, -5, -1. Okay, cool. We set those right. And I go down through and, Chrissy, what do I see in terms of my contrast?
It looks like we have some pretty good evidence for the contrast.
Okay, so what's my p-value for my contrast?
So since we have a violation of homogeneity, it looks like 0.033.
Okay, see there, fool you once. Yeah, right. We do have evidence of violation of homogeneity variance, and so when we go down and take a look at this, and it looks like, consistent with our hypotheses, that we do have at least some evidence for higher levels of negative affect among our negative profile relative to the combination of our interpersonal and benevolent. Specifically, it looks like we're getting about a 2-point increase in terms of our in the sort of point estimate of sort of change in negative affect. Now again, is that a huge difference?
Not really.
Not really, right? So again, wanting to take some of this into context. Now what I would probably want to do here is go through and want to calculate a confidence interval around that. SPSS doesn't give it to us automatically, so that's kind of a pain. But what do I need to calculate my confidence interval, right? So I'm going to want point estimated difference, 1.964 plus or minus. What do I need now?
Standard error.
Standard error. What's my standard error? Do I need to do anything to calculate my standard error here, Chris?
They give you a standard error.
They do give us a standard error,
That-
and that's fantastic. Don't make more work for yourself, right? This is the standard error for this, so we'll call it 0.911. Beautiful. What do we need now?
The critical value.
Yeah, do we have a critical value?
Is it the T?
Yeah, well, is it a T?
I'm gonna guess it's not that.
Not that T. What
Yeah.
is the T that we're getting here?
Oh, it's just the T value.
That's my test statistic,
Yeah.
right? I need a critical value, right? And so if I need to get a critical value, what do I need?
The table, yeah.
I need a table, if I'm sort of a hipster old school dude, right? Or what can I do?
Use the internet.
Use the interwebs, right? But outside of the interwebs, what do I also need in terms of to calculate a critical value?
The degrees of freedom.
Degrees of freedom. What are my degrees of freedom going to be for this?
Do we do it for the whole enchilada?
Well, so you've got a test. You've got a. Take a look at that table and tell me if you.
Oh, it's right there.
Yeah, what is it?
It is 330.
What's that? Is that the test that you interpreted?
Oh, it's not. Oh, whoa, that is a lot. 99.796.
Yeah. So. Okay. Now, so we've got. Is there anything weird about that degrees of freedom?
It's a lot lower than the one if we assume equal variances.
Yeah. And why is that? I can just fire your questions. I'm just gonna pick on you, I guess, for the rest of the hour.
That's fun. Is it because we are less free when we use the Welch's test?
Well, what it means is that, so we have a violation of homogeneity of variance, right? So we have to use, what SPSS is doing is it's using an adjusted. What are you doing? What's it? Oh,
It's
okay.
not, I was just confused as well.
I was like, so I was watching videos or something like that. Sorry I bore you. So we got a violation of homogeneity of variance, which suggests that T distribution that we calculated doesn't fall in the same T distribution as sort of what we would expect based on degrees of freedom, right? And so this adjustment is calculating an adjusted degrees of freedom. Now the adjusted degrees of freedom here is a point estimate, right? Or as a decimal. It's 99.8 degrees of freedom. We're often not going to find, you can find calculators that accept decimal degrees of freedom. Your Excel calculator will do that. But this one won't, that I've just pulled up. So what degree of freedom should we put in there?
100?
You giving yourself an extra 0.2 on degrees of freedom? Go down to 99,
Oh,
right?
okay.
So the more conservative estimate. Now, if this ever makes a difference in the universe, I'll give you $5, and it won't. But in terms of reporting what degrees of freedom that you're using, right? So here, it's telling us that our critical value with 99 degrees of freedom, 1.984. So we'll drop this 1.984, which gives us an interval estimate of 0.156 to 3.771. Okay. And then if we go through, so this is our interval estimate. Okay. What else do we want to calculate here? Effect size, right? What are our options, Kristen, for our effect size here?
You can do G.
Yep. Right.
Which is unbiased G.
Do we need unbiased G?
I don't know.
We've got 200 and some people in one group, 100 and some people. I don't know that we need a correction for small sample stuff. Okay, so we're good. But G, I think, is good, right? And so what are we going to use for our standardizer? What's that? Pooled variance. Why, and Nick, why are you thinking pooled variance? Unequal sample sizes, right? And what else? Violation of homogeneity variance, right? So we've got a lot of stuff going on, okay? So we could go through and grind out, well, let's do it. So we go down through and we based on my output here. Okay. So my pooled variance is going to be 137 times 5.187 squared plus 119 times 5.773 squared plus 74 times 7.302 squared all over 138 plus 120 plus 75 minus 3. Okay. We'll see where I'm getting that from. All right. And this is going to give me a pooled variance of 35.144. Okay. So, Nick, I think that was brilliant in terms of what we should use in terms of a standardizer, right? So we're calculating our G, right? We can go through and we can put in the value of our contrast, which is 1.964 over our pooled variance here. Take the square root of 35.144, which is going to give us 0.331. Okay. So again, we would say that based on the data that we've collected, we're seeing that our negative profile is scoring about a little over 3/10 of a standard deviation higher than the combination of our benevolent and interpersonal groups. Right? We say the point estimate, so this looks to be close to about a 2-point difference. However, after calculating an interval estimate, looks like population differences ranging from about 0.16 to 3.8 are supported by these data, or plausible given the data, or compatible with the data, however we want to say that. And so, just like with our effects of sex, we'd also say that, yeah, it looks like our negative profile is reporting, we do have some evidence that it's reporting, that they're reporting systematically higher levels of negative affect, but the extent to which that's any type of meaningful thing that's going to sort of manifest as something that's, so we can kind of see, starts to become questionable, right? We've got an effect size that's consistent with a small effect, right? Sort of low end stuff, we can go through and actually calculate, I don't think I did here, but we can calculate a confidence interval around our effect size. Now, be careful, if I get a confidence interval for my point estimate that's here, and an effect size estimate that sort of contains 0, what do we do with that? Yeah.
Chuck it.
What do we know about confidence intervals around effect size relative to confidence intervals around mean differences? We're using non-central distributions. They're not. Your point estimate isn't in the dead center of your confidence interval, right? We're using things that are skewed. Also, confidence intervals around effect sizes are going to tend to be much wider than the confidence intervals around our mean statistics, right? What we don't want to do is start to conflate effect sizes with hypothesis tests and whether or not that point estimate contains 0 and it gets you spun out of control, right? What we would probably say, and it's possible, I don't know, this is the effect size, the confidence interval for that probably doesn't contain 0. We got large enough effects, right? But what we would say is our estimate of effect, this is our best guess, but it could be fairly precise in terms of sort of what that actual population effect might be. Questions about any or all of this? Okay, the one thing, we went through, calculated all of our pooled variance for this contrast, but notice that this contrast contained all three levels of our profile factor, right? Anybody looking at this value, does this come up anywhere in our output?
This are mean squared.
Yeah. Your mean squared error, the one-way ANOVA, your mean squared error is just pooled variance. Even though for these data we have unequal cells and we have unequal variances. The mean squared error for the one way is just the pooled variance across my individual cells. You can save yourself a little bit of time. Now, if I were to want to compare the negative group and the benevolent group and leave out the interpersonal, would it make sense to just hijack the mean squared error? No, because it's possible that interpersonal is somewhere in between. Like, I don't know, what all of that sort of happens. The interpersonal group is actually, I think, the high, the most people in that group relative to the others, right? But I think it's worthwhile. Yeah, that's the highest cell size. But it's worthwhile to kind of understand what that mean squared error is, right? In the one-way ANOVA, the mean squared error is just the pooled variance for all of the cells, right? So thinking about things critically, knowing how things sort of fit together, just a kind of an FYI thing. Okay. So based on these data, we might say that yes, we have some evidence. So I would qualify this as maybe moderate evidence of differences in negative affect across sex and across belief profile. Talk about effect sizes and things like that. Say, yeah, it looks like we have evidence. These data are probably moderate evidence against the null hypothesis of equal levels of negative affect across these different groups, with the caveat that based on our interval estimates, right, it looks like we might have questions about the extent to which these data support practical differences in men and women in terms of negative affect or across these different belief profiles. Yeah, it looks like there are some elevations, but our effect sizes tend to look pretty small. Our point estimates look to be not maybe something would be consistent with sort of practical or meaningful effects or sort of things that one might see. Sort of using this all to kind of wrap this up and tie it together. Okay. Questions? Okay, cool. Let's jump into our last set here, and this is going to be the sort of this is going to be our conservatism set. It'll be our last handout here. Okay. So what we have here are fictional data. I can't remember what these were, or I screwed around with them. But the idea is that we are social scientists interested in the impact of gender differences or low-hanging fruit in terms of categorical variables. So once again, looking at gender differences across religious affiliation and sex in terms of reported conservatism. Okay. So we're social scientists and we're interested in, do we see, what are the unique and interactive effects of people's biological sex and so their religious affiliation relative to how their general endorsement of sort of conservative beliefs, things along these lines, okay? And so what we have is we have some scale of conservatism ranging from 1 to 10. We have men and women in the sample, and then we have people who identify with no religious affiliation, people who identify as Catholic, people who identify as Protestant, and people who identify as Jewish, okay? And so what we want to look at is whether or not we have unique and interactive effects within this data, and we're just open to, so this is completely exploratory, we just want to just check it out and see kind of what happens, okay? So we're sort of following along, just sort of general. So what type of design are we looking at here? 2 by 4, okay? And how many unique cells do we have? 8, right? Is screening this data fun? No. No, it's not, right? And so once again, thinking about like as my design starts to get larger and larger and larger, not only is it kind of a pain in my ass to go through and actually sort of navigate and try to interpret and things along those lines, it's also sort of hard to get, like if I have 8 different cells, right? Now all of a sudden I have to populate so some meaningful number of people within each one of those cells, things start to get very difficult, right? So the size of my sample starts to get very large, so we want to be careful with that. But what we're going to do is we're going to assume that these data are fine. So we're going to go down and we're going to say generalized linear model, univariate, conservatism is our outcome, gender, religious affiliation, options, homogeneity variance descriptives, estimates of effect size, ask for marginal means for these just because it's kind of handy sometimes, just eyeball something quick. Hit continue, and then that's all we need. Okay. So you guys hit paste, I'll hit OK. All right. So once again, we see that we have a semi-unbalanced design, not as well, not as bad as it has been in the past, but they're still not super balanced. Alicia, do I have violations of homogeneity of variance in this design? Nope. Looks like, at least in terms of conservatism, these groups are looking at least like these individual subpopulations. And these do represent individual subpopulations of people, right? But it looks like in terms of our conservative, our measure of conservatism, it's all, things are looking reasonably similar. Okay. Now, what about, Kristen, what am I seeing in terms of my effects?
We are seeing, we're not seeing any effect of religion or gender. There may be some evidence of an interaction effect between gender.
So we have some evidence of a possible interaction of gender and religious affiliation on the endorsement of conservatism stuff. Okay. What is that interaction mean?
In terms of conservative reports, there is an interaction between gender and religion.
Okay. If we wanted to develop like a meaningful interpretation of this interaction before we even look at anything, what can we? How might we interpret this? Yeah, Alicia.
The effect of gender on religion is conditioned on.
Think about it. You're on the right track. You're on the right track. We want to keep our IVs and our AVs
Yeah,
straight.
sorry.
So give it another shot.
The effect of religion or conservatism on gender.
Okay, close. So you say I would switch them around, right? So I would say the effect of differences or the effect of religious affiliation on conservatism differs by gender, right? Or we could say differences in conservatism across different religious affiliations are conditioned on gender, dependent on gender. Or we could flip around, right? We would say gender or sex differences in conservatism are dependent on religious affiliation, right? Either one of those is a reasonable way to say they're interchangeable, right? And so what it really depends on is in terms of thinking about like sort of what makes the most sense. Do I say, and I tend to think about this in terms of the baseline effect, right? For this, if we think about so if we just think about it, if I told you two things, if I told you one of two things, if I said, hey, levels of conservatism differ across men and women, or I said, hey, there are differences in conservatism across different religious affiliation, which one of those is going to be more surprising to you? Or less surprising, maybe? I'd probably say gender differences, right? We tend to see men being more conservative than women in general. Right, is that reasonable? I don't know, you might, sure, I'm not. But you do, whatever,
I was
live
just
your
looking
best
at
life.
the main effect, and it looked like religion seemed to be more,
Yeah.
more
so-
associated with it.
And that's a great catch. Oftentimes, how we frame this is going to be based on the main effect that we've got, right? If we've got a main effect of religious affiliation, then it's easier to talk about sex having an impact on differences in conservatism across religious affiliation, as opposed to the opposite, to say, oh, their religious affiliation impacts the sex differences in conservatism. Like, well, I'm looking at the manufacturers, there are no differences across sex in terms of conservatism. Well, probably they get washed out, right? But particularly when we get into regression models, so it's often if we don't have strong a priori hypotheses for ways to talk about it, that can be a nice way to go through and frame something. But if we're running interactions, we should probably at least have some sort of idea on how we want to talk about that, right? So we could do it either way here. So we do have evidence, and so this is an important thing, right? Remember we talked about the possibility of having interaction effects with no main effects? We got it right here, right? So what do we do the first time, as soon as we see that we have an interaction effect? Plot it, graph it, right? And so here, what we can do is, right, I've already done this, right? Excel is your friend in terms of graphing these things out. I can go up and I can go double click here. Right. Copy and paste that. This helps make sure that I don't have weird typographical errors. Oops. Copy that. Paste that in, right. So it's the same thing I had already done there. But I can go through now, highlight this, insert, use bar graph. Okay. Do I like this graph? Who likes this graph? Who doesn't like this graph? You don't like it. You like it the other way, Chris?
Yeah.
Like that?
I think so. Isn't that kind of what we were guessing? Is that it would differ more?
Yeah, so we would see, so, and if we wanted to talk about it sort of as that differences in conservatism are across different religious affiliations varies depending on men and women, then yeah, this is probably how we should go through and look at it. Now in terms of visually and helping me identify sort of what's going on,
The better the other way.
this kind of helps, right? So then it's just pairwise comparisons that I'm looking at, right? But I've got a screencast video where I sort of in the past when we have not had time to do it, and like going through, and this is how I presented it, right? Either way could be defensible. Again, we didn't have any a priori hypotheses, right? And in this case, I might go the other way just because visually it allows people to sort of go through and pair that. And so again, thinking about what makes the most sense. Now, if I had strong a priori hypotheses that this was sort of what I wanted to model, then this is how I should go through and graph that. But if we didn't, we could go sort of either way. Okay, so it's kind of a semantic presentational issue, but okay. All right. So how many comparisons, how many meaningful comparisons do we have within this interaction? A lot. Let's see.
18.
So we've got 1, 2, 3, 4, right? So we have 4. So if we're saying so yeah, I think it's 16. Let me see. So we got male versus female, or how many different religious affiliations? 4. So there's 4, right? Now within male, we got 1, 2, 3, 4, 5, 6. We got 6 within there. And so then by definition, 6 six within there, gives a total of 16 possible pairwise comparisons. Okay, people see where I got that from? Now we have 8 times 7 over 2. It's 56 divided by 2. 28? Okay. 28. So there's 28 physically possible pairwise comparisons that could be made, right? And this is important why we don't go through this post hoc test. You have 16, right? But if I use post hoc test, it's going to correct for 28, right? And that is going to go through and compare Jewish men and atheist women. I don't know that that's a reasonable comparison to make in terms of stuff, right? I don't know what that means. So it starts to become important that you go through and with these interactions and start to say, okay, where are the interactions, what are the comparisons that we can make, okay? Now, did we have any a priori hypotheses about what was going on here? No, right? So we just kind of did this, and now it's falling into our lap, and now we have to make something of it, right? What are our options in terms of trying to tease apart this interaction?
Post hoc test?
So yeah, some post hoc tests. So we could just tukey it up, right? I mean, if we wanted to. And trying to think about what R we would use if we wanted to use a modified tukey, right? If I set R equal to 6, that's going to control for 15 tests. And that's too small. If I had R equal to 7, 21 tests, right? That's not, it's sort of hard to get kind of in the middle there. What else did we talk about in terms of post hoc testing procedure? We just LSD it and pretend like that it's and just head forward, right? Benjamin Hochberg, right, is something I kind of like here. We've got a lot of tests that we want to go through, and what we want to do with this many tests, this is where it starts to become important that, yeah, we do have to go through and make some sort of correction, because otherwise, yikes, right? Things are going to start popping up, right? So there's a couple different things that I want to do that can start to sort of cut down on the number of tests that I am going to go through and conduct here. So I've got, so someone help me, and in SPSS, how can we break this down and test this? So we've got, what tests might be easy to do pretty quickly? If we're conducting pairwise tests.
Pairwise for,
What's that?
like, pairwise testing for which ones? Is that what which
Yeah.
ones?
Yeah.
Bunch of t-tests?
Bunch of t-tests, yeah, and we're going to do a bunch of t-tests, right? What are the t-tests that are going to be easiest for SPSS to give us right away?
Can you do repeated measures?
No, these are all individual different, so no repeated measures. What's that?
Independent t-test?
Independent t-test, right? What happens if I split this file by religious affiliation? Then what are my comparisons going to be? Male and female cross religious affiliation. Is that an easy thing to do? Cool, let's start with that, right? Okay, so if I go through and I say, I'm going to analyze, go to, that's not going to be what I want. If I go to data, split file, and I Chris, what is this gonna, or CJ, what is this gonna do as soon as I split this file by religious affiliation?
Separated based on religion.
Separated based on religion. And so now if I go through, and what should I be doing now if I want to start jumping into this first set of comparisons? Yeah, I go to independent sample t-test, and I look at conservatism across gender, 0, 1, continue there. What's it going to happen when I hit, what is it going to give me when I hit OK here?
There.
What's that?
There.
No, that's hopefully not. Right? What is it going to give me tomorrow? A bunch of t-tests. So I'm going to be comparing men and women within each religion, right? So again, if I go back to my table, it's going to give me 1, 2, 3, 4 t-tests comparing men and women within each religious affiliation. Okay. So if I go through and I
So
do
you
that.
have, so males are 1 and females are 2.
Oh, okay. Thank you. There means independent sample t-tests. There we go. So yes, someone that like really know that it was going to give me an error. Did you?
Yeah.
Oh, okay.
I tried to catch it in time without interrupting you, but I don't think I did.
No, that's fine. Anyway, so I was like, haha, you guys are funny, but right. All right. So we went through and did this, right? And so this gives me 4 of my comparisons, right? I go through. We don't have any violations of homogeneity of variance here, so I have 4 people who didn't identify a religious affiliation, men and women, or people who identified as Catholic, men and women who identified as Protestant, men and women who identify as Jewish men and women. Okay. So that gets part of it. What do I need to do now? I got 12 more of these to do.
Can you split file and then do
Split file by what?
by religious affiliation and then do one-way ANOVAs?
What's that? Okay, well, I could do that.
But you don't want to do that.
Well, what did I split file for these analyses?
Gender.
Is gender my split file or gender my DV?
Oh, right.
Okay, so what do I want to split file by?
Gender.
Gender.
Yeah.
Okay, so what we want to do here is go to data, split file. Now by gender, I'm going to organize by output just to separate this up a little bit. I'm going to hit OK. And now I'm going to go to Analyze. And I'm going to go through and conduct a one-way ANOVA model for conservatism across religious affiliation. And ask for descriptives, homogeneity, Welch, continue. So, Christian, what is this going to give me?
This is going to give you levels of conservatism by gender.
Levels of conservatism across what grouping variable? What's my DV?
Religious.
Or IV, religious affiliation, for men and for women separately, okay? And so what I'm going to do this, because what I want to see is, do I have, for men and for women, differences in conservatism across religious affiliation? When I look at my one-way ANOVA, I don't see any differences across men and women, or across religious affiliation for men, right? For the males in my sample, religious affiliation looks fairly similar, irrespective, or conservatism looks relatively similar, irrespective of religious affiliation, right? So, really, do I need to go through and like compare individually among men atheist versus Catholic, atheist, Protestant, atheist, Jewish, Protestant, Jewish, like all that stuff.
Yeah, this is covered.
Yeah, it kind of covers it, right? Now for the Benjamin Hodgberg, do I still have to count the fact that I ran these anyway? Yeah, probably, right? But this would go through and take a look. If I go down and take a look at, for the women in my sample, that yes, in fact, it does look like there are differences. For women, it looks like there are differences in religious affiliation. So this is saying that it looks like part of this interaction is looking like that maybe that we have started to see differences in religious or in conservatism across different religious affiliations, specifically among women, whereas among men, they look fairly similar to stuff. Right? So this is starting to help sort of break some of this down. But when I'm doing my Benjamin Hodgberg, remember that I need to go through and have pairwise comparisons for everything I've done, because this is post hoc, and I've already looked at the names that I can't just say, oh, that chunk is 6, I'm going to clean out because I didn't really look at those. Well, I need to still work those in, right? So what I can do, if we go through and I say, analyze, and I need to look at independent sample t-test, okay? And I'm looking at conservatism, actually here, so we're looking at conservatism across religious affiliation, right? And so I'm gonna just leave 1 and 2 in there, just as a paste, so I'm gonna hit continue and paste this into a syntax file. Alright, never mind. If I look at my syntax file, the stuff that's posted on your handout there, if we look at the top, so here what I've done is I've sorted cases by religion, right? So I'm looking at the comparison of men and women specifically within each religious affiliation. And those were my t-tests that I had gotten on the one end. But then what I'm going to do is I'm going to go through and split file by gender, right? And here was my one-way ANOVA that said that for my men, religious affiliation didn't seem to have an impact on conservatism. But for women, it did, right? But I still got to go through, if I want to perform the Benjamin Hodgberg, I need to have all t-values and p-values for all 16 of these. And so what I can do is I've got my command in my syntax file for a t-test for religion across groups 1 and 2. And then I can just take that, copy and paste it, and say for groups 1 and 3, for 1 and 4, for 2 and 3, for 2 and 4, for 3 and 4. What this is going to do, as soon as I split that file, is it's going to go through and run this individually for all of these comparisons. People see what's happening here. So if I go through and I sort this just so, and then I sort cases and split file by gender. So it's a lot, right? So I've got men, my overall ANOVAs that didn't turn out. But then, okay, so for my t-test, I've got none versus Catholic for men, none versus Catholic for women, none versus Protestant for men, none Protestant for women, none Jewish for men, none Jewish for women, Catholic Protestant men, Catholic Protestant women, sort of so on and so forth. What I've done is I've run all of these analyses, right? And so if I'm going to put together my Benjamin Hodgberg, we won't do this because I don't want to spend a bunch of time just having you watch me cut and paste things. But what I can do is I can go through and say, okay, these are my different comparisons. You want to make sure that you're labeling this in some way that makes sense, right? So I've got a test. So I've got for my, these are all my sex differences, my sex contrasts that I put in across my different religious affiliations. So people who report no affiliation, men, women, Catholic, men, women, Protestant, men, women, Jewish, men, women. T-tests, p-values. Okay? And these are just things that I cut and pasted from my output into my thing here, right? Then I've got for men, none Catholic, women, none Catholic, men, none Protestant, female, none Protestant, sort of going down through in there, right? I've got all of my individual t-tests, all of my p-values, and sort of my 16 tests here. Okay. People see what I did, how I got that. Now what I'm going to do, remember for Benjamini-Hochberg, is I want to order these in terms of sort of least evidence to greatest evidence. Okay? So I'm going to go through and I'm going to just go through, I'm going to freeze this top pane just so it doesn't move around on me. Okay? And then I'm going to go through and I'm going to sort this. Largest to smallest. See, yeah. Okay. So now I've got, it looks like my p-value is the largest for no affiliation versus Catholic men is the smallest test, and the largest test is for our women are none versus Catholic in terms of conservatism. So what I'm going to do now, go through insert. I'm going to call this index. Let's say this is my 16th test, my 15th test, so on and so forth. 16, 15, 14. There we go. Drag that down. Okay. So what I've got is I've got this index here. And then what I can do with my Benjamini-Hochberg, my Benjamini-Hochberg p-value is going to be equal to my index divided by the number of tests that I have. How many tests do I have? 16 times my alpha level. What's my alpha level? 0.15. Okay. So what I'm going to do is then take this and just drag this down. And I can go through, format this. Okay. So, looking at this, Chris, which of these tests would I register as something that meets the threshold for continued interpretation for stuff here?
Primarily in the interaction between female and religion. So those bottom three.
Okay, what about this? Is this one?
No.
No. Okay. So it's just going to be these two. Okay. So with Benjamini-Hochberg is going to say, in terms of talking about this interaction, really the only two of these 16 comparisons, the only one that are sort of providing compelling evidence or convincing evidence above and beyond stuff that's just going to be like type 1 error or false positive rates are going to be the contrast of unaffiliated, religiously unaffiliated women versus Protestant women and unaffiliated women versus Catholic women in terms of differences in terms of overall conservatism, right? And so based on these analyses, what we might say is that based on these, it appears that level of differences in conservatism across individuals of different religious background looks to be conditioned on sex, right? So sort of the differences that we're seeing in conservatism across religious affiliations depends on whether or not we're talking about men and women. Right? Now for men, it appears that level of conservatism looks to be relatively similar irrespective of religious affiliation. But for women, it looks like there are differences. Predominantly what we're seeing is differences among religiously unaffiliated women and women who identify as Catholic, and religiously unaffiliated women and women who identify as Protestant in terms of the main difference there, right? And so if we go back and take a look at our Chris C was right. I'm gonna go back to and swap this around. Okay. And also another thing too, we want to think about our scaling here. That scaling is a 0 to 10 scale, right? Not a 6.6 to 8 scale. That makes it look a lot more different than it is. Okay. So what we're seeing here, in terms of men, regardless of religious affiliation, men are all looking about the same, right? However, when we look at women, it appears that we do see the interaction that we're seeing is a function of unaffiliated women having less conservative views as compared to Catholic and Protestant women. Are sort of the comparison among non-affiliated and women identified with Judaism sort of not sort of reliably different, at least within this set, right? And if we wanted to, in our Benjamini-Hochberg, to go through and sort of expand this out, what we could do is then go through and for these last two, this is where I said, remember when I sent you that thing like, hey, don't do this, that's not a good use of this, not making you calculate confidence intervals and effect sizes for a bunch of stuff that doesn't make any difference, right? But what we see here is we see effect sizes that are quite large for these two that got flagged. Effect size of 0.74, effect size of 0.94, the confidence interval, or excuse me, sort of differences in units of conservatism. And again, this is a 1 to 10 scale, so you got about a full point difference there. That seems reasonable. Our effect sizes 0.6, 0.8, so medium to large effects. Confidence intervals here, confidence intervals are an point estimate of effect. And so we can use this to start talking about, yes, it looks like based on these data that differences in conservatism across different religious views is dependent on participant sex. And what's kind of going on is that for men, it looks like conservatism, levels of conservatism are pretty consistent, right, or comparable. But for women, we do see differences, specifically the strongest evidence for differences in unaffiliated women versus Protestant, for women who identify as Protestant, and unaffiliated women relative to those who identify as Catholic. Go through, make interpretations of those, and then call it good. How are people feeling? So, this is a big interaction, right? And a big interaction that we had no a priori idea about what was going to go on. And so there's a lot of stuff to go through and try and figure out. But this is why it's important to have a good game plan on the front end before you jump into the mix with stuff. Okay. Questions about this? Yes.
With the output, like when running the independent simplest t-test, is it fine if like males and females are in the same t-test?
What do you mean?
Like yours was split up male and then they had t-test and then female.
Oh yeah. That's. I mean, if I were to go through and run the same thing, except with if I were to run this, it's just going to look different. If I go through data and go to split file and compare groups like that, and then I go through and run it, and then if I run the same thing, it's gonna sort of change how the format is, but it's still going to be the same stuff. Yeah. Other questions? Okay. This will be complicated and this will be difficult, and you'll run into snags, and sort of it's easy to get turned around when you're trying to figure out these interaction effects. If you have questions or you're kind of think you have a plan but you're not solid on whether or not that's a good plan, or you're having trouble verbalizing why you might do that, talk amongst yourselves, see if you can get it straightened out, come talk to me, or to Laura, to try and avoid spending, a couple hours doing something that turns out to be kind of down the wrong rabbit hole and having to turn around and do it. So if I don't tell you to run a screening on something, you don't have to run a screening on something. So I won't have you do 2 screenings, so if you don't have to do another one, don't worry about that. Email help for Laura's, no, Laura's not worried about this. For my mental health, and for bonus points for having things well organized and presented so that I can find things, so trying to make sure that the organization is good. Remember that if we're talking about confidence intervals, we need to have some sort of indication that you recognize we're talking about population differences, we're talking about effect sizes. I want you to have some sort of meaningful effect going on in there. Use S values, base factor, that helps you to make arguments, but you don't feel like you have to go through and do that. Omega squared is preferable to eta squared statistics, unless you've got unbalanced designs, which you might have throughout this whole thing. So just keep an idea on that. But that should get you squared away with stuff. Okay. All right. Thanks, folks. A good semester. I like the way with these changes, things have turned out. I think you guys have done a really nice job. I think sort of forcing us to think about practical differences and not just yes, no decision making is sort of really shown up as sort of more considered and careful interpretations and thinking about some of these data, which I think is a good thing. But thanks for hanging with me. This is the first time we've done all this stuff, so you guys were guinea pigs. So thank you for that. If you haven't filled out evals, do that. I think those close down on